Heat treatment of steel. Full annealing. Full annealing is a heat treatment process applied to steel to reduce hardness, increase ductility, and relieve internal stresses. It involves heating the steel to 30-50 degrees Celsius above its upper critical temperature. Heat 3 for hypotectoid steels, or slightly above the austenitic temperature for other steels, and holding it at this temperature for a sufficient time to transform the microstructure completely to austenite. This is followed by very slow cooling, typically in the furnace, to allow for the formation of a coarse pearlite microstructure, which contributes to the desired softness and ductility. Key characteristics: purpose, reduce hardness, increase ductility, relieve internal stresses, improve machinability. Process: heating above upper critical temperature. At 3 for hypotectoid steels, or austenitic temperature, followed by slow furnace cooling. Microstructure: coarse pearlite. Stress relief. Stress relieving is a heat treatment process used to reduce residual stresses in materials, particularly in steel, that may have been introduced during manufacturing processes such as welding, machining, casting, or cold working. These residual stresses can lead to distortion, cracking, or premature failure of the component. The process typically involves heating the steel to a temperature below its lower critical temperature. Acts 1. Usually between 550 degrees Celsius and 650 degrees Celsius for steel parts. The material is held at this temperature for a specific soaking time, which allows the atoms to rearrange and relieve the internal stresses, without causing significant changes to the microstructure or mechanical properties. Like hardness, after soaking, the material is cooled slowly, often in air, to prevent the reintroduction of new stresses. Key characteristics: purpose, reduce residual stresses, prevent distortion and cracking, improve dimensional stability. Process: heating below the lower critical temperature. Acts 1. Holding for a period, and then slow recrystallization. Recrystallization is a heat treatment process that restores ductility and removes the effects of work, hardening, strain hardening in metals, particularly after cold working. When a metal is cold worked, its grains become deformed and elongated, leading to increased strength and hardness, but reduced ductility. Recrystallization involves heating the deformed metal to a specific temperature range, known as the recrystallization temperature, where new, strain-free grains nucleate and grow, replacing the deformed ones. For steel, recrystallization annealing typically occurs below the PSK line, in the range of 550 degrees Celsius to 700 degrees Celsius. The exact temperature depends on the specific steel alloy and the degree of prior cold work. During this process, there are no lattice transformations, phase changes, as seen in full annealing. The primary goal is to recover the material's ductility and toughness without significantly altering its overall composition or other mechanical properties. Key characteristics: purpose, restore ductility, remove effects of work hardening, reduce hardness, improve formability. Process: heating cold work metal to its recrystallization temperature, allowing new strain-free grains to form. Temperature range: for steel, typically 550 degrees Celsius to 700 degrees Celsius, below the lower critical temperature. Effect: formation of new equiaxed, strain-free grains, increased ductility, and reduced hardness. Spheroidizing. Spheroidizing is a heat treatment process primarily applied to high-carbon steels, typically those with more than 0.8% carbon, to improve their machinability and cold formability. The main objective is to transform the lamellar, plate-like, or network carbide structures, cementite, FAC, into a globular or spherical shape, dispersed within a ferrite matrix. This globular form of cementite reduces the hardness and brittleness of the steel, making it softer and more ductile. The process generally involves heating the steel to a temperature just below, at or slightly above the lower critical temperature, X1, typically in the range of 650 degrees Celsius to 770 degrees Celsius. The steel is held at this temperature for an extended period, allowing the cementite to coalesce into spherical particles. This is followed by slow cooling, often in the furnace or air, to maintain the spheroidized structure. Key characteristics: purpose, improve machinability, enhance cold formability, reduce hardness and brittleness. Process, heating to a temperature around the lower critical temperature. X1, prolonged holding and slow cooling. Temperature range, typically 650 degrees Celsius to 770 degrees Celsius. Microstructure, spheroidal carbides, cementite dispersed in a ferrite matrix. Application, high carbon steels, tool steels, and alloy steels. Normalizing is a heat treatment process applied to steel to refine its grain structure, relieve internal stresses, and improve its mechanical properties, particularly toughness and ductility. It is often used to homogenize the microstructure of steel that has been subjected to various manufacturing processes, like hot rolling, forging, or casting, which can result in non-uniform grain sizes and internal stresses. The process involves heating the steel to a temperature above its upper critical temperature, as at 3 for hypoetectoid steels, or above the upper critical temperature, as at M for hyperetectoid steels, typically 30 to 50 degrees Celsius higher than the annealing temperature. The steel is held at this temperature for a short period to ensure complete austenitization, and then cooled in still air at room temperature. The air cooling rate is faster than furnace cooling, used in annealing, but slower than quenching, resulting in a finer and more uniform grain structure, and a harder and stronger material compared to annealed steel. Key characteristics: purpose, refine grain structure, relieve internal stresses, improve toughness and ductility, homogenize microstructure. Process, heating above the upper critical temperature, acet 3 or acetim, followed by cooling in still air. Microstructure, finer perlite and ferrite, for hypoetectoid steels, or finer perlite and cementite for hyperetectoid steels, compared to annealed steel. Effect: increased strength and hardness, improved toughness and ductility, more uniform microstructure. Hardening of steel. Hardening of steel is a heat treatment process that significantly increases the hardness and strengths of steel. This process primarily relies on the transformation of austenite into martensite, a very hard and brittle microstructure, through rapid cooling quenching. The general steps for hardening steel include austenitizing. The steel is heated to a temperature above its upper critical temperature, ATS 3 for hypotectoid steels or ATSM for hypoeutectoid steels, to transform its microstructure entirely into austenite. The specific temperature and holding time depend on the steel's composition, especially carbon content and the desired final hardness. Sufficient time must be allowed for carbon to dissolve uniformly in the austenite. Quenching. After austenitizing, the steel is rapidly cooled, quenched in a suitable medium such as water, oil, polymer solutions, or forced air. The rapid cooling prevents the formation of softer microstructures like perlite or bainite, and promotes the diffusionless transformation of austenite to martensite. The cooling rate must be faster than the critical cooling rate for the specific steel to achieve full hardening. Factors influencing hardening. Carbon content. Carbon is the primary alloying element responsible for the hardenability of steel. Higher carbon content generally leads to higher achievable hardness. Alloying elements. Elements like chromium, molybdenum, manganese, and nickel increase hardenability by slowing down the transformation of austenite to pearlite and bainite, allowing for slower quenching rates to achieve martensite. Quenching medium. The choice of quenching medium affects the cooling rate and thus the final hardness and residual stresses. Water provides the fastest cooling, followed by oil and then air. Part size and shape. Larger or more complex parts may experience non-uniform cooling, leading to variations in hardness and potential distortion or cracking. Martensite, while very hard. Quenching. After austenitizing, the steel is rapidly cooled, quenched in a suitable medium such as water, oil, polymer solutions, or forced air. The rapid cooling prevents the formation of softer microstructures, like pearlite or bainite, and promotes the diffusionless transformation of austenite to martensite. The cooling rate must be faster than the critical cooling rate for the specific steel to achieve full hardening. Factors influencing hardening. Carbon content. Carbon is the primary alloying element responsible for the hardenability of steel. Higher carbon content generally leads to higher achievable hardness. Alloying elements. Elements like chromium, molybdenum, manganese, and nickel increase hardenability by slowing down the transformation of austenite to pearlite and bainite, allowing for slower quenching rates to achieve martensite. Quenching medium. The choice of quenching medium affects the cooling rate and thus the final hardness and residual stresses. Water provides the fastest cooling, followed by oil and then air. Part size and shape. Larger or more complex parts may experience non-uniform cooling, leading to variations in hardness and potential distortion or cracking. Martensite, while very hard, is also very brittle. Therefore, hardening is almost always followed by a tempering process to reduce brittleness and improve toughness, albeit at the cost of some hardness. Key characteristics. Purpose. Increase hardness and strength. Process. Heating to austenitizing temperature followed by rapid quenching. Microstructure. Primarily martensite. Affect high hardness and strength, but increased brittleness. Tempering of steel. Tempering is a heat treatment process that is almost always performed after hardening quenching of steel. The primary purpose of tempering is to reduce the brittleness of hardened steel and improve its toughness and ductility, while still retaining a significant portion of its hardness and strength. Hardened steel, which contains a high percentage of martensite, is very hard, but also very brittle and susceptible to cracking. The tempering process involves reheating the hardened steel to a temperature below its lower critical temperature, a T1, typically ranging from 150 degrees Celsius to 700 degrees Celsius, 300 degrees Fahrenheit to 1300 degrees Fahrenheit, depending on the desired properties. The steel is held at this temperature for a specific period, allowing for the controlled decomposition of martensite into more stable and ductile microstructures, such as tempered martensite, bainite, or fine carbides dispersed in a ferrite matrix. After holding, the steel is usually cooled in air. Key effects of tempering. Reduced brittleness. The most significant effect is the reduction of internal stresses and the transformation of brittle martensite into a tougher, more ductile structure. Improved toughness and ductility. The ability of the steel to absorb energy before fracture increases, and its capacity for plastic deformation improves. Slight decrease in hardness and strength. While the primary goal is to improve toughness, there is an inevitable trade-off, and some hardness and strength are sacrificed. The higher the tempering temperature, the greater the reduction in hardness and strength, but the higher the toughness. Relief of internal stresses. Tempering helps to relieve the residual stresses introduced during quenching, which can prevent distortion and cracking. The specific tempering temperature and time are crucial, and are carefully selected based on the steel composition and the desired balance of properties. For the final application, key characteristics. Purpose. Reduce brittleness. Improve tough. Key characteristics. Purpose. Reduce brittleness. Improve toughness and ductility. Relieve internal stresses. Process. Reheating hardened steel to a temperature below AQ1, holding and then cooling, usually in air. Temperature range. Typically 150 degrees Celsius to 700 degrees Celsius. Microstructure. Tempered martensite or fine carbides in a ferrite matrix. Effect. Increased toughness and ductility. Decreased brittleness. Slight reduction in hardness and strength. Isothermal transformation diagrams. TTT diagrams. Isothermal transformation diagrams, commonly known as TTT, time temperature transformation diagrams, are graphical representations that illustrate the kinetics of phase transformations in steel at a constant temperature. These diagrams are crucial for understanding how different microstructures like perlite, bainite, and martensite form from austenite when steel is cooled and held isothermally at a constant temperature below the eutectoid temperature. Key features and interpretation of a TTT diagram. Axis. The horizontal axis represents time, often on a logarithmic scale, and the vertical axis represents temperature. C-curves nose. The diagram typically consists of several C-shaped curves. These curves mark the start and end of specific phase transformations. For example, austenite to perlite, austenite to painite. The nose of the C-curve represents the shortest time required for a transformation to begin. Transformation products. Different regions on the diagram correspond to different microstructures that form at various temperatures and times. Perlite forms at higher temperatures, just below the eutectoid temperature, and longer times. It is a lamellar mixture of ferrite and cementite. Bainite forms at intermediate temperatures, below the perlite nose, but above the martensite start temperature. It has a finer, needle-like structure. Martensite forms when austenite is cooled rapidly enough to bypass the perlite and bainite transformations. It is a diffusionless transformation that occurs below a specific martensite start, Mies temperature, and continues down to a martensite finish. MF temperature. Martensite formation is time independent. Austenite stability. The area above the C-curves represents the stable austenite phase. Austenite stability. The area above the C-curves represents the stable austenite phase. How TTT diagrams are used. TTT diagrams are used to predict the microstructure that will form in a steel alloy when it undergoes an isothermal heat treatment. By selecting a specific temperature and holding time, engineers can control the transformation products and thus the final mechanical properties of the steel. For example, to obtain a fully perlitic structure, the steel would be cooled rapidly to a temperature within the perlite region and held until the transformation is complete. To obtain bainite, it would be cooled to a lower temperature in the bainite region. It is important to note that TTT diagrams are specific to a particular steel composition and are developed under isothermal conditions. For continuous cooling processes, continuous cooling transformation (CCT) diagrams are more appropriate. Key characteristics. Purpose predict phase transformations in steel at constant temperatures. Components, time temperature axes, C-shaped curves indicating transformation start and end, regions for perlite, bainite, and martensite. Application, designing isothermal heat treatments. to achieve desired microstructures and properties. Cooling curves superimposed on TTT diagram. While TTT isothermal transformation diagrams are developed under isothermal conditions, constant temperature, they can be used to approximate the microstructures formed during continuous cooling processes. By superimposing cooling curves onto the diagram, this allows for a visual representation of how different cooling rates affect the transformation products of austenite. How it works. A cooling curve, representing the temperature change over time during a continuous cooling process, is plotted on the same TTT diagram. The curve starts from the austenitizing temperature and proceeds downwards. As the cooling curve intersects the start and finish lines of various transformations on the TTT diagram, it indicates which microstructures will form and at what temperatures and times. Critical cooling rate. A crucial concept derived from superimposing cooling curves is the critical cooling rate. This is the minimum cooling rate required to completely bypass the perlite and bainite noses on the TTT diagram and achieve a fully martensitic microstructure. A cooling curve that is tangent to or passes to the left of the nose of the perlite. T curve represents the critical cooling rate. Interpretation of superimposed cooling curves. Slow cooling, for example, furnace cooling curve, will intersect the perlite start and finish lines, resulting in a perlitic microstructure. The slower the cooling, the coarser the perlite. Moderate cooling, for example, Forward cooling. A moderate cooling curve might intersect the perlite region, leading to a mixture of perlite and potentially some bainite, if it also passes through the bainite region. Fast cooling, for example, forward cooling, oil or water quenching. A fast cooling curve, if it bypasses the perlite and bainite noses and reaches the martensite start mese temperature, will result in a martensitic microstructure. The faster the cooling, the more likely it is to form martensite. Limitations. It is important to note that superimposing continuous cooling curves on TTT diagrams provides an approximation. TTT diagrams are strictly for isothermal transformations. For more accurate predictions of microstructures under continuous cooling conditions, continuous cooling transformation, CCT diagrams are specifically designed and are more appropriate. Key characteristics. Purpose: approximate microstructure formation during continuous cooling using isothermal data. Method: plotting cooling rate curves on a TTT diagram. Concept: critical cooling rate to achieve martensite. Limitation: provides an approximation. CCT diagrams are more accurate for continuous cooling. Continuous cooling transformation. CCT diagrams. Continuous cooling transformation. CCT diagrams are graphical representations that show the transformation behavior of austenite in steel during continuous cooling, as opposed to the isothermal holding conditions of TTT diagrams. CCT diagrams are more practical for industrial heat treatment processes, as most real-world cooling operations involve continuous cooling rather than isothermal holding. Key features and interpretation of a CCT diagram. Axes similar to TTT diagrams. The horizontal axis represents time, often logarithmic, and the vertical axis represents temperature. Cooling curves. Multiple cooling curves, representing different cooling rates, are plotted on the diagram. Each curve shows the temperature profile of the steel as it cools continuously from the austenitizing temperature. Transformation regions. The diagram shows regions where different microstructures ferrite, perlite, bainite, martensite form. As the cooling curves intersect the transformation start and finish lines, these lines are shifted to longer times and lower temperatures compared to TTT diagrams for the same steel, due to the continuous cooling effect. Critical cooling rate. On a CCT diagram, the critical cooling rate is represented by the cooling curve that just touches the nose of the perlite or bainite transformation region without entering it, indicating the fastest cooling rate that still allows for the formation of these softer phases. Any cooling rate faster than this will result in martensite formation. Differences from TTT diagrams. Cooling condition TTT diagrams are for isothermal transformations, constant temperature, while CCT diagrams are for continuous cooling. Curve shape. The transformation curves on CCT diagrams are generally shifted to the right, longer times and downwards. Lower temperatures compared to TTT diagrams. For the same steel, this is because continuous cooling provides less time for diffusion-controlled transformations to occur at any given temperature. Practicality. CCT diagrams are more directly applicable to industrial heat treatment processes, like quenching, normalizing, and annealing, where cooling is continuous. How CCT diagrams are used. CCT diagrams are used to predict the final microstructure and mechanical properties of steel components after various continuous cooling treatments. By knowing the cooling rate of a specific process, for example, air cooling, oil quenching, water quenching, one can trace the corresponding cooling curve on the CCT diagram to determine which phases will form and in what proportions. This helps in selecting appropriate heat treatment parameters to achieve desired properties. Key characteristics. Purpose. Predict phase transformations in steel during continuous cooling. Components. Time temperature axis. Multiple cooling curves and regions for different microstructures. Application. Designing and optimizing continuous cooling heat treatments for steel. Advantage. More practical for industrial applications compared to TTT diagrams. Hardenability. Hardenability is a critical property of steel that describes the depths to which a steel alloy can be hardened by the formation of martensite upon quenching from its austenitizing temperature. It is important not to confuse hardenability with hardness. Hardness refers to the material's resistance to indentation, while hardenability refers to the ability to achieve a certain hardness throughout the cross-section of a part. Factors influencing hardenability. Carbon content. While carbon is essential for achieving high hardness, it has a relatively minor effect on hardenability itself. However, sufficient carbon is necessary for martensite formation. Alloying elements. This is the most significant factor affecting hardenability. Alloying elements such as manganese, Man, chromium, Cro, molybdenum, nickel, Ni, and boron, B, increase hardenability by slowing down the rates of perlite and bainite transformations. This allows for slower cooling rates to achieve a fully martensitic structure throughout a larger cross-section. Grain size. A coarser austenite grain size generally increases hardenability because it reduces the total grain boundary area, which acts as nucleation sites for ferrite and perlite, thus delaying their formation. Homogeneity of austenite. A more homogeneous austenite, where alloying elements and carbon are uniformly distributed, leads to better hardenability. Importance of hardenability. Selection of steel. Hardenability data helps in selecting the appropriate steel for a given application, ensuring that the desired hardness and microstructure can be achieved throughout the component, especially for larger or thicker sections. Quenching medium selection. Steels with high hardenability can be quenched in less severe media, for example oil or air, instead of water, to achieve the desired hardness, which helps to minimize distortion and cracking. Cost effectiveness. Understanding hardenability allows for the use of less expensive alloying elements or less drastic quenching methods, while still achieving the required properties. Measurement of hardenability. The hardenability of steel is typically measured using the Jomini and quench test, which provides a hardenability curve showing the hardness variation along the length of a quenched bar. Key characteristics. Definition. The ability of steel to harden in depth upon quenching. Distinction. Different from hardness resistance to indentation. Influencing factors. Alloying elements. Most significant. Grain size, homogeneity of austenite. Importance. Steel selection. Quenching medium choice. Cost effectiveness. Measurement, Jomini and quench test. Jomini and quench test. The Jomini and quench test is a standardized laboratory method used to determine the hardenability of steel. It provides a measure of how deeply a steel can be hardened when quenched from its austenitizing temperature. This test is crucial for comparing the hardenability of different steel alloys and for selecting appropriate materials and heat treatment parameters for specific applications. Procedure. Specimen preparation. A cylindrical steel specimen, typically 1 inch 25.4 mm in diameter and 4 inches 102 mm long, is prepared according to ASTM, a 255 or ISO 642 standards. Austenitizing. The specimen is heated to its appropriate austenitizing temperature and held for a sufficient time to ensure complete transformation to austenite and uniform carbon distribution. End quenching. The hot specimen is then quickly transferred to a fixture where one end is quenched by a controlled stream of water. The other end cools primarily by air, creating a gradient of cooling rates along the length of the bar. The end being quenched experiences the fastest cooling rate, while the cooling rate progressively decreases along the length of the bar, away from the quenched end. Hardness measurement. After cooling to room temperature, two parallel flats are ground along the length of the specimen. Rockwell hardness measurements are then taken at regular intervals. For example, every 1/16 inch or 1.5 mm along these flats, starting from the quenched end. Results and interpretation. The hardness values are plotted against the distance from the quenched end, resulting in a hardenability curve. This curve shows the variation of hardness as a function of cooling rate. The quenched end, experiencing the fastest cooling, will typically show the highest hardness, often martensitic. As the distance from the quenched end increases, the cooling rate decreases, and the hardness generally drops as softer microstructures, bainite perlite, begin to form. A steel with high hardenability will maintain a high hardness over a greater distance from the quenched end, indicating that it can be hardened more deeply or in larger sections. Conversely, a steel with low hardenability will show a rapid drop in hardness a short distance from the quenched end. Results and interpretation. The hardness values are plotted against the distance from the quenched end, resulting in a hardenability curve. This curve shows the variation of hardness as a function of cooling rate. The quenched end, experiencing the fastest cooling, will typically show the highest hardness, often martensitic. As the distance from the quenched end increases, the cooling rate decreases, and the hardness generally drops as softer microstructures, bainite, perlite, begin to form. A steel with high hardenability will maintain a high hardness over a greater distance from the quenched end, indicating that it can be hardened more deeply or in larger sections. Conversely, a steel with low hardenability will show a rapid drop in hardness a short distance from the quenched end. Significance. The Jomini test provides a practical and reproducible way to assess the hardenability of steel. which is essential for predicting the mechanical properties of heat-treated components. It helps in selecting the correct steel for a given part size and desired properties, and in optimizing quenching processes to avoid distortion and cracking. Key characteristics. Purpose. Measure the hardenability of steel. Method and quenching a standardized specimen to create a cooling rate gradient, followed by hardness measurements along its length. Output, a hardenability curve. Hardness versus distance from quench end. Significance, helps in steel selection, process optimization, and predicting properties. Ostempering is an isothermal heat treatment process applied to ferrous metals, particularly steel and ductile iron, to produce a microstructure known as bainite. This process aims to achieve a combination of high strength, ductility, and toughness, often superior to that obtained by conventional quenching and tempering. Procedure. Austenitizing. The steel is first heated to an austenitizing temperature above ACACE 3 to transform its microstructure into a homogeneous austenite phase, quenching to isothermal temperature. Instead of quenching to room temperature, the steel is rapidly cooled, quenched to an intermediate temperature, typically between the perlite nose and the martensite start emission temperature, and held at this constant temperature. This temperature range is usually between 250 degrees Celsius and 450 degrees Celsius, 480 degrees Fahrenheit, and 840 degrees Fahrenheit. Isothermal transformation. The steel is held at this constant temperature for a sufficient period to allow the austenite to transform isothermally into bainite. This transformation is diffusion controlled and takes time, which is why TTT diagrams are particularly relevant for understanding this process. Cooling to room temperature. After the bainitic transformation is complete, the steel is cooled to room temperature, usually in air. No further transformation occurs during this final cooling step. Advantages of ostempering: improved toughness and ductility. Bainitic microstructure provides an excellent combination of strength and toughness, often with better ductility than tempered martensite at similar hardness levels. Reduced distortion and cracking. The slower cooling rate during the isothermal hold, compared to conventional quenching, minimizes thermal stresses and reduces the risk of distortion and cracking, especially in complex geometries. Good fatigue strength. Ostempered components often exhibit superior fatigue resistance. Elimination of tempering. Since bainite is formed directly, a separate tempering step is usually not required, simplifying the heat treatment process. Applications. Ostempering is commonly used for components requiring high strength and toughness, such as springs, fasteners, gears, and certain automotive parts. Key characteristics. Purpose: achieve high strength, ductility, and toughness by forming bainite. Process: austenitizing, rapid quenching to an intermediate isothermal temperature, holding for bainitic transformation, and then cooling to room temperature. Microstructure: bainite. Advantages: improved toughness, reduced distortion, good fatigue strength, no separate tempering step. Martempering. Martempering, also known as martenching, is a specialized heat treatment process for steel, designed to minimize distortion and cracking that can occur during conventional quenching, especially in complex or large parts. It aims to achieve a fully martensitic microstructure with reduced internal stresses. Procedure: austenitizing. The steel is first heated to its austenitizing temperature to transform its microstructure into homogeneous austenite. Interrupted quench. Instead of quenching directly to room temperature, the steel is rapidly quenched into a molten salt bath, hot oil, or molten lead bath, held at a temperature just above the martensite. Startman's temperature, but below the perlite and bainite noses on the TTT diagram. This temperature is typically between 150 degrees Celsius and 300 degrees Celsius, 300 degrees Fahrenheit, and 570 degrees Fahrenheit. Equalization. The steel is held in this quenching medium for a sufficient time to allow the temperature to equalize throughout the cross-section of the part. During this holding period, no transformation of austenite occurs, as the temperature is above Ms. Slow cooling to room temperature. After equalization, the steel is slowly cooled in air from the molten salt bath to room temperature. As the temperature drops below MZ, the austenite transforms into martensite. The slow cooling through the martensite transformation range allows for a more uniform formation of martensite and helps to relieve internal stresses, thereby reducing distortion and cracking. Tempering. Martempering is almost always followed by a conventional tempering process to improve the toughness and ductility of the martensitic structure, as martensite is inherently brittle. Advantages of martempering: reduced distortion and cracking. The primary advantage is the significant reduction in thermal stresses and volume changes during the martensitic transformation, leading to less distortion and cracking compared to conventional quenching. Improved dimensional stability. Components treated by martempering exhibit better dimensional stability, suitable for complex geometries. It is particularly beneficial for parts with intricate shapes or varying cross-sections that are prone to distortion during rapid quenching. Applications. Martempering is commonly used for tool steels, dies, gears, and other precision components, where dimensional stability and minimal distortion are critical. Key characteristics. Purpose: minimize distortion and cracking. During hardening, achieve martensitic microstructure with reduced internal stresses. Process: austenitizing. Interrupted quench to a temperature just above MZ. Equalization: slow cooling to room temperature, followed by tempering. Microstructure. Martensite. Advantages: reduced distortion, improved dimensional stability, suitable for complex parts. Case hardening. Case hardening, also known as surface hardening, is a heat treatment process that creates a hard, wear-resistant surface, the case on a steel component, while maintaining a tough, ductile, and relatively soft core. This combination of properties is highly desirable for parts that need to withstand surface wear and abrasion, but also require resistance to shock loading or bending without fracturing. Case hardening is typically applied to low-carbon steels, carbon content generally below 0.25%, or low alloy steels, which do not harden significantly throughout their cross-section when quenched. The process involves introducing carbon, nitrogen, or both into the surface layer of the steel at elevated temperatures, followed by quenching and often a low-temperature tempering. General principle: enrichment of surface layer. The steel part is heated in an atmosphere rich in carbon carburizing, nitrogen, nitriding, or both carbonitriding. At high temperatures, these elements diffuse into the surface of the steel, increasing the carbon and or nitrogen content in the outer layer. Hardening of the case. After the diffusion process, the part is quenched. Because the surface layer now has a higher carbon-nitrogen content, it can be hardened to a significant degree, often forming martensite upon quenching, while the low-carbon core remains relatively soft and tough. Tempering optional but common. A low-temperature tempering step is often performed after quenching to relieve stresses and improve the toughness of the hardened case, without significantly reducing its hardness. Advantages of case hardening. Wear resistance. The hard surface provides excellent resistance to wear abrasion, and fatigue. Tough core. The soft core maintains ductility and toughness, preventing brittle fracture. Cost effective. Allows the use of less expensive low-carbon steels for applications requiring a hard surface. Common case hardening processes, carburizing, introduction of carbon into the surface, nitriding, introduction of nitrogen into the surface, cyaniding, introduction of both carbon and nitrogen, using cyanide salts, carbon intriding, introduction of both carbon and nitrogen, using gaseous atmospheres, flame hardening, surface hardening, using a flame, induction hardening, surface hardening, using electromagnetic induction, vacuum carburizing, plasma nitriding. Advanced methods for case hardening. Key characteristics. Purpose. Create a hard, wear-resistant surface with a tough ductile core. Application. Low carbon steels and low alloy steels. Mechanism. Diffusion of carbon and or nitrogen into the surface at high temperatures, followed by quenching. Advantages. High wear resistance, good toughness, cost effective. Carburizing. Carburizing is a thermochemical case hardening process in which carbon is diffused into the surface of low carbon steel, typically with less than 0.25% carbon, to increase its surface hardness and wear resistance. The core of the material retains its original low carbon content, thus remaining tough and ductile. Process heating. The steel parts are heated to an austenitizing temperature, usually between 850 degrees Celsius and 950 degrees Celsius, 1560 degrees Fahrenheit, and 1740 degrees Fahrenheit, in a carbon-rich atmosphere. Carbon diffusion. At these high temperatures, carbon atoms from the surrounding atmosphere, for example, carbon monoxide gas, solid carbazine compounds, or liquid saltpeter, diffuse into the surface layers of the steel. The longer the time at temperature, the deeper the carbon penetration. Quenching. After the carbazine cycle, the parts are quenched, rapidly cooled in oil, water, or polymer solutions. The high carbon content in the surface layer allows it to transform into hard martensite upon quenching, while the low carbon core transforms into softer microstructures like ferrite and pearlite. Tempering. A low temperature tempering process, typically 150 degrees Celsius to 200 degrees Celsius, is usually performed after quenching to reduce brittleness and relieve stresses in the hardened case, improving its toughness without significantly reducing its hardness. Types of carbazing. Gas carbazing uses a carbon-rich gas atmosphere, for example, natural gas, propane, or endothermic gas, in a furnace. Packed carbazing. Parts are packed in a solid carbazine compound, for example, charcoal, barium carbonate, and heated. Liquid carbazing. Salt bath carbazing. Parts are immersed in a molten salt bath containing carbon-donating compounds. Vacuum carbazing, performed in a vacuum furnace, offering precise control and cleaner surfaces. Applications. Carbazing is widely used for components requiring a hard, wear-resistant surface and a tough core, such as gears, shafts, bearings, cams, and automotive components. Key characteristics. Purpose. Increase surface hardness and wear resistance of low-carbon steel. Mechanism. Diffusion of carbon into the surface at high temperatures. Result. Hard martensitic case. Tough low-carbon core, commonly followed by quenching and low-temperature tempering. Nitriding. Nitriding is a thermochemical case hardening process that diffuses nitrogen into the surface of steel to create a very hard, wear-resistant, and corrosion-resistant surface layer. Unlike carburizing, nitriding is typically performed at lower temperatures, which minimizes distortion and eliminates the need for subsequent quenching and tempering. Process heating. Steel parts are heated to a temperature range of 480 degrees Celsius to 570 degrees Celsius, 900 degrees Fahrenheit to 1060 degrees Fahrenheit, which is below the lower critical temperature, XE1 of steel. Nitrogen diffusion. The parts are exposed to a nitrogen-rich atmosphere. Nitrogen atoms diffuse into the surface of the steel, reacting with alloying elements, such as aluminum, chromium, molybdenum, and vanadium, to form stable nitrides. These nitrides are extremely hard, and are responsible for the increased surface hardness. Cooling. After the nitriding cycle, the parts are typically cooled slowly in the furnace or in air, since the process occurs at relatively low temperatures, and no phase transformation is involved. Distortion is minimal. Types of nitriding. Types of nitriding. Uses ammonia gas, NH, highs, as the source of nitrogen. Ammonia dissociates at the steel surface, releasing atomic nitrogen that diffuses into the steel. Salt bath nitriding, liquid nitriding. Parts are immersed in a molten salt bath containing nitrogen-donating compounds. Plasma nitriding, ion nitriding, performed in a vacuum chamber, where a plasma containing nitrogen ions is generated. This method offers precise control over the nitrided layer and is environmentally cleaner. Advantages of nitriding. High surface hardness. Produces very high surface hardness, leading to excellent wear and abrasion resistance. Improved fatigue strength. The compressive residual stresses induced in the nitrided layer enhance fatigue resistance. Good corrosion resistance. The nitrided layer can improve corrosion resistance. Minimal distortion. Low processing temperatures minimize dimensional changes and distortion, making it suitable for finished or near-finished components. No quenching required. Eliminates the need for a separate quenching step, simplifying the process. Applications. Nitriding is commonly used for precision components that require high wear resistance, fatigue strength, and dimensional stability, such as gears, crankshafts, valve parts, dies, and tooling. Key characteristics. Purpose. Create a very hard, wear-resistant and corrosion-resistant surface layer. Mechanism. Diffusion of nitrogen into the surface at relatively low temperatures, forming hard nitrides. Result. High surface hardness, improved fatigue strength, minimal distortion, no subsequent quenching or tempering required. Cyaniding. Cyaniding is a thermochemical case hardening process that simultaneously introduces both carbon and nitrogen into the surface of steel. It is a rapid and effective method for producing a hard, wear-resistant case on steel components, particularly for small to medium-sized parts. The process is typically carried out using molten cyanide salts. Process heating and immersion. Steel parts are immersed in a molten salt bath containing cyanide compounds, for example, sodium cyanide, sodium carbonate, sodium cyanate, at temperatures typically ranging from 870 degrees Celsius to 950 degrees Celsius, 1600 degrees Fahrenheit to 1740 degrees Fahrenheit. For high temperature cyaniding, or lower temperatures, around 550 degrees C 850 degrees C, for low temperature cyaniding. Carbon and nitrogen diffusion. At these elevated temperatures, carbon and nitrogen atoms from the molten salt bath diffuse into the surface layers of the steel. The carbon contributes to the formation of carbides, and nitrogen forms nitrides, both of which contribute to the increased surface hardness. Quenching. After a specified holding time, the parts are removed from the salt bath and quenched in water or oil. This rapid cooling transforms the enriched surface layer into a hard martensitic structure. Rinsing. The parts are then thoroughly rinsed to remove any residual cyanide salts. Tempering. Optional. A low temperature tempering may be performed to improve the toughness of the case and relieve stresses. Advantages of cyaniding. Rapid case formation. Cyaniding is generally faster than carburizing for achieving a given case depth. High surface hardness produces a very hard and wear-resistant surface. Improved fatigue strength. The combined effect of carbon and nitrogen diffusion enhances the fatigue resistance of the treated parts. Good ductility of core maintains a tough and ductile core. Disadvantages and safety concerns. Toxicity. The use of cyanide salts makes the process highly toxic and requires strict safety precautions, proper ventilation, and waste disposal procedure. Toxicity. The use of cyanide salts makes the process highly toxic and requires strict safety precautions, proper ventilation, and waste disposal procedures. Environmental impact. Environmental regulations often restrict or prohibit the use of cyanide processes due to their hazardous nature. Due to the significant safety and environmental concerns, cyaniding has largely been replaced by less hazardous processes like carbonitriding and nitriding in many industrial applications. Key characteristics. Purpose. Produce a hard, wear-resistant case by simultaneously introducing carbon and nitrogen. Mechanism. Diffusion of carbon and nitrogen from molten cyanide salt pass. Result. Hard surface, improved wear resistance and fatigue strength. Safety. Highly toxic process with significant environmental concerns. Replacement. Largely superseded by carbonitriding and nitriding. Carbonitriding. Carbonitriding is a thermochemical case hardening process that simultaneously introduces both carbon and nitrogen into the surface of steel. It is essentially a modified carbonizing process, where ammonia NH is added to the carbonizing atmosphere to provide nitrogen. This process is particularly effective for low carbon and low alloy steels, offering a hard, wear-resistant surface with improved hardenability and fatigue strength compared to carbonizing alone. Process heating. Steel parts are heated to an austenitizing temperature, typically lower than that used for carburizing, ranging from 700 degrees Celsius to 900 degrees Celsius, 1300 degrees Fahrenheit to 1650 degrees Fahrenheit. Carbon and nitrogen diffusion. The parts are exposed to a controlled atmosphere containing carbon-donating gases, for example, methane, propane, and ammonia. At elevated temperatures, carbon and nitrogen atoms diffuse into the surface layers of the steel. The nitrogen enhances the hardenability of the case, allowing for less severe quenching media and reduced distortion. Quenching. After the diffusion cycle, the parts are quenched, usually in oil, to transform the enriched surface layer into hard martensite. The presence of nitrogen in the case allows for a slower cooling rate to achieve the desired hardness, which helps in minimizing distortion. Tempering. A low-temperature tempering step is typically performed after quenching to relieve stresses and improve the toughness of the hardened case. Advantages of carbonitriding. Improved hardenability. Nitrogen increases the hardenability of the case, allowing for less severe quenching and thus reducing distortion and cracking. Higher surface hardness. Can achieve higher surface hardness than carburizing for certain applications. Enhanced wear resistance. The combined effect of carbon and nitrogen provides excellent wear and abrasion resistance. Better fatigue strength. Improved compressive residual stresses in the case enhance fatigue life. Reduced distortion. Lower processing temperatures and less severe quenching contribute to less distortion compared to conventional carburizing. Applications. Carbon nitriding is widely used for small mass-produced components that require a hardware-resistant surface and good fatigue properties, such as gears, shafts, pins, and automotive components. Key characteristics. Purpose. Enhance surface hardness, wear resistance, and fatigue strength by diffusing both carbon and nitrogen. Mechanism. Simultaneous diffusion of carbon. Mechanism. Simultaneous diffusion of carbon and nitrogen from a controlled atmosphere. Result. Hard case with improved hardenability, reduced distortion, commonly followed by quenching and low temperature tempering. Flame hardening. Flame hardening is a surface hardening heat treatment process that selectively hardens the surface of a steel component using a high temperature flame. It is a localized hardening method, meaning only the areas exposed to the flame are hardened, while the core remains relatively soft and tough. This process is typically applied to medium carbon steels, 0.35-0.7% carbon, and some alloy steels that are hardenable by conventional quenching. Process. Surface heating. The surface of the steel part is rapidly heated to its austenitizing temperature using an oxy-fuel flame, for example, oxyacetylene, oxypropane. The heating is localized and quick to prevent the core from reaching the austenitizing temperature. Quenching. Immediately after heating, the heated surface is rapidly quenched, usually with a water spray or other quenching medium. This rapid cooling transforms the austenitized surface layer into hard martensite. Tempering. Optional. A low temperature tempering step may be performed to relieve stresses and improve the toughness of the hardened case. Tempering. Optional. A low temperature tempering step may be performed to relieve stresses and improve the toughness of the hardened case. Key characteristics and advantages. Localized hardening. Only specific areas requiring wear resistance are hardened, which can be beneficial for large or complex parts. Shallow case depth. Typically produces a relatively shallow hardened case, suitable for applications where surface wear is the primary concern. Minimal distortion. Due to localized heating and rapid cooling, overall part distortion is generally less than with true hardening. Cost-effective. Can be a cost-effective method for selective hardening, especially for large components, where furnace hardening would be impractical or expensive. Flexibility. Can be adapted to various part geometries and sizes. Applications. Flame hardening is commonly used for large gears, cams, shafts, machine ways, and other components that require a hard, wear-resistant surface in specific areas. Key characteristics. Purpose. Selectively harden the surface of steel components for wear resistance. Mechanism. Rapid heating of the surface with a flame, followed by quenching. Result. Hard martensitic case on the surface. Tough core. Advantages. Localized hardening, minimal distortion, cost-effective for large parts. Induction hardening. Induction hardening is a surface hardening heat treatment process that uses electromagnetic induction to rapidly heat the surface of a steel component, followed by immediate quenching. This method allows for precise control over the heated area and depth of hardening, making it highly efficient and suitable for selective hardening of specific regions of a part. Process. Inductive heating. The steel part is placed within or near an induction coil, which is connected to a high-frequency alternating current AC power source. The alternating current flowing through the coil generates a rapidly changing magnetic field. This magnetic field induces eddy currents within the surface layers of the steel part, causing rapid resistive heating, joule heating of the material. Austenitizing. The surface of the steel is quickly heated to its austenitizing temperature. The depth of heating is controlled by the frequency of the AC current, the power input, and the heating time. Higher frequencies result in shallower heating. Quenching. Immediately after the desired surface temperature is reached, the heated area is rapidly quenched, typically by a water spray or polymer solution. This rapid cooling transforms the austenitized surface layer into hard martensite. Tempering optional. A low-temperature tempering step may be performed to improve the toughness of the hardened case and relieve stresses. Key characteristics and advantages. Rapid heating. Induction heating is extremely fast, often taking only seconds, which minimizes grain growth and distortion. Selective hardening. Only specific areas of the part are heated and hardened, leaving the core tough and ductile. This is ideal for components requiring localized wear resistance. Precise control. The depth and pattern of hardening can be precisely controlled by adjusting parameters such as frequency, power, and heating time. Minimal distortion. Due to localized and rapid heating, overall part distortion is significantly reduced compared to through hardening. Clean process. It is a clean and environmentally friendly process, as it does not involve open flames or chemical baths. Energy efficient. High energy efficiency due to direct heating of the workpiece. Applications. Induction hardening is widely used for components requiring high surface hardness and wear resistance, such as gears, crankshafts, camshafts, axles, bearing races, and other automotive and machinery parts. Key characteristics. Purpose. Selectively harden the surface of steel components for wear resistance. Mechanism. Rapid heating by electromagnetic induction, followed by quenching. Result. Hard martensitic case on the surface. Tough core. Advantages. Rapid, selective, precise control, minimal distortion, clean, energy efficient.